So, as I said last time, we are trying to build representations of the formal group. It will allow us to organize our different space in a way that will be useful in order for us to talk about field theory that enjoys models and theory. Right? So that's the goal of what we're trying to do here. And along the way, we'll prove a couple of really, really interesting results. One of which will come in the next lecture, where I'll show you that demanding that our theory unitary, I was to say, without information, will put a bound on the dimension, on the scaling dimension of operators. So we'll prove that statement. It's actually a really beautiful result that is not a particularly old result, and goes back to the PhD work of Conformal. I left off last time by telling you that it will be very useful for us. So firstly, we're going to be working mostly with radial conservation, and it will be useful for us to specify how fields transform under conformal transformations, but we need only specify what happens to fields at x0. Right? So typically we're talking about fields, scalars, they could be spinors, they could be vectors. I labeled them last time generically with by phi a. That A could be living in some representation of the Lorentz group, so it could be a scalar or a spinor or tensor. Now, I said that I left off last time by telling you that we need only specify the value of this field at the origin. And where I left off was to try and convince you that we're not losing any information. Now, the role that the origin plays in this is the same as in traditional quantum field theory, where you specify things in, let's say, Schrödinger representation, and then you transform to the Heisenberg representation by acting with an exponential of the Hamiltonian. Here, the exponential is not the Hamiltonian, but rather the generator of calculations in space. So the point is that you can write field phi a x in terms of field phi field phi a origin generator momentum and the momentum generator like this. So again, this is some index vision. Spinor, scalar. This is the generator of stations. And the point here is that if I tell you how this guy transforms under the conformal transformation, then that's enough to tell you how phi A transformed at some general point in space. And for these fields located at the origin, Lorentz transformations act as follows. Now we're considering these fields as operators, and so when I talk about the action of generators, it's always by commutators. So generators of Lorentz transformations are these MUs, and they act on phi A's via the spin part of the transformation, B, that's it. The point here is that this transformation, this action of the Lorentz generators on the field of the origin, just contains a spin part of the transformation. And we said last time that the transformation comes in two parts. There's the spin part and there's the orbital. The orbital part is generated by just one element of the conformal group for all the different fields, and the spin part is different for each representation of the fields. So this has a different value if you're talking about spinner, it has a different value if you're talking about scalars, it has a different value if you're talking about vectors. So then it's kind of natural to ask at this point, have we lost some information? We lost some information in specifying the transformation just on fields located at the origin. It certainly doesn't contain the orbital part. The answer is actually no, including one. So the fact that only the spin part appears in this transformation is direct consequence of the fact that Lorentz transformations in the origin invariant. Okay, kind of by definition of the Lorentz transformations and how they act in the method. So the question we ask here is, have we lost any information? I would like to say things like, without loss of generality, I'm asking, have we lost any generality? So my point is this, that knowing this is sufficient to write down the most general transformation law. To see why, let's know the following. So suppose I consider some general operator. So I don't really care what the operator is. So here, for example, this is the generator of Lorentz transformation, but it could be any operator. So let's ask how that operator acts on a field phi A at some general point X. Let's say that operator is O, and it's acting on field phi A at the point X in space. And this is some arbitrary operator. By definition of a commutator, this is O A of X minus phi A of X O. This is e to the phi X of P e to the minus phi X of P O by A O e to the I x p phi A the origin e to the minus I x p minus e to the I x dot p phi A the origin e to the minus phi x p times O e to the I x dot p e to the minus phi x dot p. But then I can take out e to the I x p on the left of this term and this term. So e to the I x dot p. What's left is this term times this minus this times this term. So the commutator between those two. E to the e to the minus I x dot p O e to the I x dot p I A the origin e to the minus I x dot p. Let's look at this moment. Point is that if I know how this guy transforms, then I'm able to build up how this guy transforms. So in particular, if I choose O be the generator of growth transformations, I use the comparative problem. Verify that e to the minus x dot p of m nu e to the I x dot p we can show is just m nu minus x nu p nu plus x nu p mu. Then the following is true. Using this in here with O chosen to be M nu, find that action of the Brooks generator on phi A and x is e to the I x dot p . . the commutator minus 5x p u e to the I x p commutator with 5 a naught e to the minus 5x p. Moving on equal to e to the minus x dot e times the commutator of m nu minus x nu e nu plus x nu e nu commutator with 5a dot multiplying e to the minus x dot e. Well, this guy commutated with this is just that. This is e to the minus x times sigma nu a b by b naught p nu acts like a derivative with this factor I. So p nu commutated with x8 so that I minus I, so that makes this plus I x nu du by a naught minus I x nu du by a naught, or applying to the minus I by a naught. We could adjust sigma nu a b by b naught. That's right at x. Plus 5x nu du by a x, thinking of this guy as an operator itself. Right. Plus minus I x nu du by a x. Okay. So indeed, it's not just the spin path that appears. We don't lose information. We don't lose any information by just specifying the transformation properties of the field at the origin. Okay. I pick up exactly this kind of commutator that I would expect at some arbitrary point x. We have not lost any information in just sticking to fields at the origin. The next question we need to ask is, okay, so we haven't lost any information by restricting our attention to fields at the origin, but remember, we're interested in transformations that keep the origin invariant. Okay, so the question is, what transformations, what subset of the conformal transformations leave the origin invariant? So, which conformal transformations? These zero variant. Well, to answer this, let's go to our expression for a general conformal killing vector. Because this is really where we encode all the symmetries that we're talking about. We're talking about conformal symmetries, they're encoded in the structure of the conformal killing vector, which we get by solving the conformal killing equation, which encodes symmetries in the structure. So yeah, the general conformal killing vector, psi mu, could be written as a mu, so plus translating vector, plus omega mu nu, x nu, plus scalings, plus special conformal transformations, encoded in the b mu squared minus 2 x mu b dot x. Okay, again, translations. Rotations, variance transformations, the rotations, boost, scalings, and special conformal transformations. Okay, so that's a general conformal killing vector. The question is, what set of conformal transformations keep the origin x equals 0 invariant? Well, conformal transformations that leave the origin invariant are those for which psi is 0 when x is 0. Okay, so then we have to ask when if we impose that psi is 0 when x is 0, what does that mean? So I mean x equals 0. Well, I said x equals 0 everywhere. And the only term that remains is the translations. And setting this equal to 0 means that the translations must be 0. So the set of conformal transformations that leave the origin invariant are those for which a mu equals 0. But there's no restrictions on Lorentz transformations, there's no restrictions on scaling, there's certainly no restrictions on special conformal transformations. All of those stay. So the set of conformal transformations that leave the origin invariant are those that look like this. Okay? Good. So scalings, Lorentz transformations, and special conformal transformations all leave the origin invariant. So now let's follow what we would have done, first course of quantum mechanics. And remember, what we're trying to do is use representation theory to organize the Fox space state in this conformal field. Right? So what you would have done in quantum mechanics, first course of quantum mechanics, is you would use you would label states by the eigenvalues of some operators that you're interested in. So spin operators, magnetic operators, etc. So if you're going to solve the I don't know, let's say hydrogen atom, right? Then you would find that you have orbital angular momentum and spin angular momentum, and you use the spin angular momentum operator and the orbital angular momentum operator to label the states that you're acting on, right? So the eigenstates would be states that, the states that you're interested in are eigenstates of these operators, okay? And the eigenvalues will give you the good quantum number space. So we want to play the same game here. Okay. The question, of course, is which operators should we use? Well, we're going to come up with a set of operators that are kind of fundamental to this whole story, and these are the operators that we've made a throwaway statement about earlier, the primary operators in the conformal field. These are the operators that have the lowest scaling dimension possible. And all the other operators we get by basically more or less taking combinations of the primary operators and all their derivatives. Okay, these are called secondary operators or descendant operators. And once we know the story that we're building is that once we know what the primary is in any conformal field theory is, that's it. We know all the data we need to know about the CFT. Of course, if it was that simple, then everything about the conformal field theory could be known by now, but it's not. It turns out that finding all the primary operators in the conformal field theory is A, very difficult, and B, largely an unsolved problem. And a very small set of conformal field theories, mostly pre-conformal field theories, that we know what the primary operators are. But once we know those primary operators, we know everything we need to know about the conformal field. Okay, so we haven't even gotten to the juicy part, which is correlation functions. And there again, we'll find that once you know the correlation functions of the primary operators, that's it. You can get all the other correlators by just acting with derivatives of the correlated primaries. So these are very important operators. That's what I want to go to now. Point is that the operators that we choose now to organize our Fock space need to be simultaneously diagonalized. Now you go back to maybe linear algebra, but definitely in your first course of quantum mechanics, and you remember that simultaneously diagonalizing operators, matrices are simultaneously diagonalizable if and only if they commute with each other. So we need to find operators, generators from quantum mechanics, that commute with each other. Well, one we know off the bat, and this is the fact that the dilatation operator and the generator of the Lorentz transformations and mu commute with each other. It's part of the algorithm. So, two, organize the states of CFT. Good. Quantum numbers. Yeah, borrowing terminology from quantum mechanics. You got labels. States. This corresponds to finding operators that we can simultaneously diagonalize. First set of operators that simultaneously commute are the generator of dilatations and the Lorentz transformations. Yeah, this is part of the algebraic structure of a conformal. Then I can say, well, these guys, ME and U's, satisfy some complicated algebra, right? The algebra of Lorentz generators. And they're plus sign, but they're minus sign, but you remember there's 4 terms, 2 of them are positive, 2 of them are negative. Maybe somewhere in there, some subset of these MUs are going to commute with each other. Right? So I can pick some set of M's that the right hand side of the complicated algebra structure will be 0. No, this is certainly not going to be true for all of the M's, right? The M's, if I take generically MU commutated with M lambda sigma, the right hand side is not going to vanish. But there's some subset of the M's for which they will vanish. So what we do is, following what we would do in quantum mechanics, is you pick a maximum commuting subset. So you can see where I'm going here. Right? Where I'm going is that I want to set up labels. These labels are the eigenvalues associated to these operators. What are the eigenvalues associated to the taken operator? It's a scaling dimension. Right? What are the eigenvalues associated to the Lorentz generators? Typically it's spin, because I'm going to be able to relate these things to some simple group like SU2. Okay, so now I have spin as an eigenvalue, and I have scaling dimension as an eigenvalue. What we'll find is that the states that we're interested in are states that are going to be labeled by precisely spin and scaling dimension. These are going to be the primary states on the field. Okay, so we'll just play the same game that we would in element quantum mechanics and define the pair of generators. They I have each value that this I can take. And we'll label it by plus and minus. We can define this as half epsilon I j k m j k. Remember, mu and nu go over space time indices only, not spatial indices. The I and j, right? Plus or minus I am not half. And these are summed over. Then I look at these generators, and these generators pick out some subset of the M's, and you can check that this is a maximally commuting subset. So if I take the M's that fit into here, they commute with each other, and it's the biggest subset of the total set of M's that commute with each other. Okay. And then I ask, what is the algebra satisfied by these guys? Well, these J's close an SU2 plus SU2 of the other. So remember, SU2 is a set of 2 by 2 unitary matrices with unit equivalent. Okay. So the algebra that's satisfied by these J's is SU2 cross SU2. Yeah. These are two much matrices that are unitary. Means that if U is an element of set, then U dagger U is U dagger is the identity. And satisfy that they have determinant with the one. The nice thing about these algebraic structure is that we know lots of things about SU. Okay. This again is elementary quantum mechanics because the group that angular momentum forms is precisely SU2. So everything that you learn about angular momentum in elementary quantum mechanics, or when you first learn about abstract algebras, the algebras come into play here and use this. In particular, the kinds of representations that we always look for in Lie groups are irreducible representations. So the point is important. I said that a representation of a group was the ability to write the group elements as matrices, so that I can use the algebra. Right? Which matrices do I care about? Well, I care about those matrices that I can't break down into smaller pieces. Right? That I can't, if I can diagonalize, if I can block diagonalize a matrix, then I can take the blocks and I can work with those blocks as elementary objects. But I'm interested precisely in the smallest representations, ones that can't be broken down any further. These are called irreducible representations, right? So one of the things that we know about SU2 is that every SU2 irreducible representation is labeled by a single spin. So in this case, I have one SU2 here and another SU2 here. So there are two pairs. Well, there's a pair of spins that will label the irreducible representations that I care about. Okay. So this means that each irreducible representation of the Lorentz group SO1,3 can be labeled by a pair of spins, one for each of the SU2 factors. Okay. So now we've got three numbers at our disposal. Two of them are the spins corresponding to the SU2s of the Lorentz group. And the other one is this eigenvalue of the dilatation number, which we call delta last time. Okay. So those three numbers are going to be used as labels for the states of the form field area. So the statement here is that putting these together, we can label representation of the formal group Yeah. That's it. Yeah, what? I actually had a question of the night. And the scaling dimension delta with the eigenvalue of the rarity. Okay. So, again, you can go back to quantum mechanics and figure out the allowed value of the spin that you can have, and we'll come back to this a little bit later, but just in a way of making an analysis. This should be familiar to you already. I'm not going to spend too much time on. What I am going to spend time on is this one, because this is new. Okay. So then we have to ask, well, what are the allowed values of the scaling dimensions? Can we just pick any of scaling dimensions? The answer is no. To understand why this is the case, let's make the following. So, to work out the allowed values of delta, we have the following. So an operator phi, and again, I need only tell you what happens at the origin. So an operator phi at origin has scaling dimension delta. If E acting on phi A is minus pi delta phi A 0, or equivalently IT acting on phi A of naught is delta phi A. Right. That's different. Taking on phi as an operator, and so the action of the facilitation operator on this operator is via the commutator. And again, I've talked a little bit about this in the context of states. And we know that there's a state operator corresponding to conformal field theories that can have state operators. So conceptually, what I'm about to do is not new, but for completeness, let's just do it anyway. Because we're going to need at least the manipulations in our problem. So now consider the following operator. So I'm going to take my operator phi, and I'm going to act on phi with the generator of spectral conformal transformations K. How to find operator phi tilde A, also acknowledged as K, sorry, this carries two indices. So K acting on A. And let's ask, what is the scaling dimension of this? So again, I have some operator phi A, right? And I'm telling you that this operator phi A has scaling dimension delta, which means that it satisfies this equation. Okay, its eigenvalue with respect to the rotation operator is delta. And of course, I'm kind of confusing notation here. I can always move the I around. So when I say it's just delta, I mean either of these statements, whichever makes it more comfortable. So then I take that same operator, phi A, and I act on it with generator of special conformal transformations. And I want to know what is the scaling dimension of this guy. So to do that, we need to work out the commutator of phi tilde with E. Calculate E with phi tilde in U. This is the commutator of D with the commutator of A mu phi A. But commutators are like derivatives in that they obey the product rule. And in particular, they obey a particular combination called the Jacobian identity. It says that that's by way of so the Jacobian identity of course. If I've got B operator with A, B, and C, and the commutator of A with the commutator of B and C, plus cyclic permutations, all cyclic permutations of this. So B with C A plus C with A B vanishes because everything has gone. So I have one of these guys that belong here, and I can write it in terms of the other two. So I can write this as minus commutator of K mu with phi A commutator with D minus phi A of naught with the commutator this. But I know that phi A has eigenvalue delta, and I know that these guys satisfy an algebra. These guys are part of the conformal algebra. So this is just minus I delta of K mu with phi A of naught minus I phi A of naught with K mu. And of course, these two are the same. I'll put it in the sign. So this is just minus phi delta minus 1 of phi tilde A at naught. In other words, if phi A is an operator with scaling dimension delta, then K mu commutator, K mu acting on phi A is an operator with scaling dimension delta minus 1. In other words, K mu lowers delta by 1. Okay. Let me stop there because I see the next class eager to start. Right. So what I'll show you next time is that P mu acts on phi to raise scaling dimension by 1. And between KMU and PMU, they kind of act like little raising operators that you would be familiar with from the harmonic oscillator. And we will build on that on Friday. So on Friday, the main goal is going to be to prove that delta is bounded from below.